So it's singular only in this sense. I'm not talking about singularities in the sense discussed by Moule, irregular singularities, regular singularities. Yeah, here it's just about uniqueness and existence. Okay? And here I'm essentially presenting the core part of Anya's thesis, which is on this notion of singular problems and algorithms related to that. Yeah? I will start with the general discussion of outer inverses and inner inverses, which are...
Same as Penrose inverses?
No, it's more special, but I will tell you where Penrose inverses fit in. Huh? Then we'll show you how this relates to generalized boundary problems, how you can then again introduce a multiplication on these generalized boundary problems, which very naturally is an extension of the multiplication of regular boundary problems. And again, like in the case of, I should say, plane boundary problems, corresponding result or some corresponding results on factorization, because here the situation is much more difficult. And I will, just for reference purposes, just show you some of the algorithms, or at least in the slides, they will be there for reference purposes. Okay? So, and if there's still time left, yeah, if William wants me early enough, or if I keep looking at this clock there, I will try to come back very briefly to the part that I missed in the previous talk about an application to actuarial mathematics, which is maybe a nice conclusion. So, what is, first of all, a generalized inverse? Because that's maybe easier to capture. So, we take now again just vector spaces over K, V and W. And again, please think of cases like if T is the nth differential operator iterated n times, then this would be a map from Cn to C, n times differential function to continuous function. So that's the function spaces we are thinking of here. So we have an operator, linear operator T from V to W. Then G will be called an inner inverse, naturally, if T, G, T is T. So G occurs here at the inner position. Yeah? There's unfortunately a Babylonic confusion of terminology here. So that's also called a quasi-inverse, a semi-inverse, a whatever inverse. There are many names. Yeah? But I think that Zuha Neshet, who is one of the authorities for generalized inverses, who wrote or edited a book which is this thick, yeah, came out in '76. Yeah, he suggested that the best would be to just call it an inner inverse, because that's really natural, and I agree. Yeah? So I call it an inner inverse if the G occurs here in the inner position. TGT is T. An outer inverse, naturally, if GTG is equal to G. And you see that if G is a one-sided inverse, then immediately it will be both an inner and an outer inverse. So this is a generalization. It's even more general than a one-sided inverse, being an inner inverse or being an outer inverse. Okay? And therefore, a one-sided inverse will also be a generalized inverse, because a generalized inverse is something which is both an inner inverse and an outer inverse. Yeah? So that's called a generalized inverse, or if you want to be precise, an algebraic generalized inverse, because the word generalized inverse is also used when V and W has some additional structure, topological vector spaces, locally convex, Hilbert, whatever, yeah? And then there are corresponding notions of generalized inverses, but here I'm using the naked vector space setting. So that's a generalized inverse. Yeah? And they always exist. Yeah? And not only do they exist, but they exist really in abundance. Yeah? And you can construct them in the following way. Yeah? So the two crucial subspaces for a linear map are the kernel and the image, yeah? Because the kernel measures how well it does with respect to injectivity. Yeah? And if this is big, it means it messes up a lot. Yeah? Then we have to fix it by choosing a complement to this kernel space here. Yeah? That's the kernel complement. I call it here B, because typically when T is the differential operator, these are boundary conditions. Okay? Or more precisely, the space of admissible functions corresponding to the boundary conditions. And there's then a projector corresponding to this direct decomposition. And similarly for the image, which measures how well it does with respect to surjectivity, If it doesn't reach the full space, we just add, for fixing that, a complement here. And again, we have a projector Q according to this direct decomposition. Okay? And then you can think morally that this generalized inverse, it first projects onto Q to make sure that we are in the image, and then we just take the restriction of T as an operator from B to the image. That's one we can invert, and that's going to be the generalized inverse, okay? And if you do it more precisely, then you have to take care that, well, the projector P, for instance, or 1 minus P, yeah, that's a complementary projector. It can be split into the part that does the real work, yeah, that's the surjection that projects onto this P, and then you just have to an inclusion into V. Yeah? And the same for the other projector, yeah? And also this restriction is another map tau, which you can invert, and then the original map is a composition of this projection, then this bijective part, and then the inclusion, and the generalized inverse will be the opposite. Yeah? It projects onto the image, then undoes the tau here, and then includes it back into the vector space V. Okay? So that's the generalized inverse. And since you asked about the Moore-Penrose inverse, or Penrose inverse, that's a special case when the vector space has the additional structure of an inner product. Okay? Then you can choose canonical complements here, namely the orthogonal complement, and also here the orthogonal complement, and then with that choice, this will be the Moore-Penrose inverse. Okay? In particular, if it's a Hilbert space, and you also have a topology, yeah, then you have a notion of generalized inverse. Yeah? But here it's more general. I can, and also if you have a Hilbert space, you can of course forget the inner product. Yeah? Right. You can choose any projector here, meaning you can choose any complements there, and you get a generalized inverse corresponding to this choice of projectors. And it turns out that this is a bijective correspondence. Yeah? So for every choice of P and Q, there's exactly one generalized inverse. Okay? So Moore-Penrose is a special case. So that's quite easy to understand, the case of generalized inverses. Outer and inner inverses are generalized inverses. Yeah? They are more general, yeah? Because clearly every inner inverse, every generalized inverse is of course both of these. Yeah? So what's now an outer inverse? So it's, of course the definition is here, yeah? But to really understand it, yeah? How can you characterize it? Well, the point is this, yeah? In a generalized inverse, you choose a complement of the kernel, and this complement will at the same time be the image of your generalized inverse. And likewise, you choose a complement of the image, and this complement will be the kernel of G. That's somehow the canonical choice. Yeah? And now, we can just say that we do only one of these. Yeah? If we want to solve TU equals F, yeah, in the generalized inverse setting, then you enforce uniqueness. You enforce the uniqueness of...
checking the software now.
Yeah.
Yeah. Sorry.
No problem, yeah? If you have a double problem here, yeah? If you want to solve TU equals F, the solution may not exist, and for a certain F it may not be unique, yeah?
Right.
So you can fix uniqueness by adding a constraint on the U, and the constraint will be that the U must be in this space B, yeah? And this is a constraint.
B, okay.
Yeah, this is a constraint. This can be described by boundary conditions. Yeah, but these are functionals on B, and these will be constraints on the U. Yeah? So U in B is equivalent to saying that the beta of U is 0 for all elements beta in the curly B. Okay. So uniqueness is fixed by adding constraints, and these constraints are described by this B here. And existence is ensured by removing exceptions, because for some F this may not be solvable, so you just remove them by replacing the F by correcting it, by subtracting from it some F tilde, and these F tilde are the bad guys, so to say, from the exceptional space. E is the space of exceptions. These we just remove, yeah? And then we get a solution. Okay, so that's the situation of generalized inverses. And now for the outer inverse, we say, okay, yeah, we will use the B here as the image of G, and the E as the kernel of G, but instead we just stipulate that the kernel of T need only be disjoint from B. It need not be, like here, a direct sum with V. It need only be disjoint. So in particular, we can make it a lot smaller. This B can be much smaller than here, just so that it is big enough so that, big enough so that it's disjoint. Can be 0, So 0 is always an outer inverse, Not a very useful one, But GTG equals G, If G is 0, it's an outer inverse, That's right, Not a useful one, but it is one. Good, So we have possibly a smaller space here, and since a smaller space means that we add more conditions, we have more constraints, So the calligraphic B, which is the orthogonal, will be larger then, So that means we have more constraints. And at the same time, we modify the second constraint. Instead of saying that W should be a direct sum of the image of T and E, we just say that, no, it needn't be the full image here. It's only the image of B under T here, okay? And that means that this here has become smaller. That's not the full image, it's just the image of B that has become smaller, and that means the E has to become larger. So we have more exceptions. So it's somehow fair, We have more constraints, but we have also more exceptions. That's the idea of the outer inverse. So, and if you look at these conditions, you see that the second condition involves both the B and the E. So if you choose your B and E, you first should choose B, so that it satisfies that. And then for this choice of B, you have, again, various choices for E. That's the second choice you make. And then, of course, you come back to the case of the generalized inverse if you choose a maximal B. If you choose the B as big as possible so that this becomes a direct sum, and that means you use only as many constraints as necessary, not more than necessary. Okay? So the idea of the outer inverse is then that you make this T smaller as compared to the generalized inverse. You make it smaller by shrinking this bijective part. That's the bijective part of the map that goes from the image of B to this complement of the kernel. And now you make it even smaller because, as I said, this B becomes smaller and this T of B correspondingly becomes smaller. So it's a contraction of the generalized inverse, and one can check that this leads to the following direct sums. This one we had already, and this one is the one that comes from this condition, if you so to say improve it a bit. That's the direct sum here, and these two direct sums of the two vector spaces V and W correspond again to some projectors, and again this pair of projectors corresponds to a unique outer inverse, and it does the same thing. You first project onto this T of B here, and then you can use this bijection here inverted. That's the generalized. That's the outer inverse. I write it here with this symbol. The outer inverse corresponding to P and Q, which is again in bijective correspondence. And you can also parameterize it instead of the projectors P and Q, of course, also with the choice of these two spaces P and E. Okay, so that's the outer inverse. An inner inverse is, of course, just a dual situation. So G is an outer inverse if and only if T is an inner inverse. So, but still, as often in mathematics, when you have two concepts which are dual to each other, formally it's very symmetric, but the properties can be rather different, like product, co-product. And again, here with inner inverses, the situation is this. For generalized inverses, we had these four relations, the two direct sums, and the identity B equals image G, E equals kernel G. And in that case, what we do is we keep the direct sum, but we give up the fact that the B must be exactly equal to the image of G and E must be exactly equal to the kernel of G. So we just keep these direct sums. And now we select an arbitrary map A, linear map from E to V. So E is this exceptional space where our inverse can, so to say, do whatever it wants. So we can choose this by specifying this map A, and that's supposed to extend the bijective part of our map. Okay? And again, here, this direct decomposition here can be described with two projectors, and then the inner inverse will be a direct sum of these. Yeah? On the exceptional part, we do what is prescribed here, and on the other part, we just invert this bijection. Okay? And again, I can parameterize this in terms of projectors and in terms of the spaces here, but in addition, I have to specify this map A. So here I'm doing the opposite, yeah? Because if you look here, the E will in general be bigger than the kernel of G, right? Because of this extension here, what has formerly been 0, this can now be something non-zero because the A can do something with it. Yeah? And also B is now smaller than the image of G in general. Yeah? And that means, if you look here, yeah, the B, what the G really does is more than the B. Yeah? And that means it's fewer constraints, yeah? Because the constraints are always the opposite. Yeah? So we need fewer constraints, but also, because of that here, fewer exceptions. Yeah? What the G really does, yeah, the inverse, yeah, is smaller than the E. Yeah? So we don't use all the exceptions, we use fewer exceptions. So in that sense, it's the opposite of the philosophy of the outer inverse. And if you choose A equals 0, then you just get back to the generalized inverse. Okay? Yeah, as I said, yeah, this is just dual to each other. And for boundary problems, we actually need outer inverses. Yeah? So I don't need the concept of inner inverse. I just wanted to mention it here because it belongs together. Okay, huh? Maybe for time reasons, I will not spend time on this finite dimension and codimension here. Fredholm operators are nice because generalized Green's operators are always Fredholm operators. So that means that the dimension of the kernel is finite and also the codimension of the image is finite. Yeah? And this is, so to say, preserved. Yeah? Okay. Yeah? And what I told you about the evaluation matrix can be generalized because in the regular case, we really check a direct sum. And now for an outer inverse, we just want to check disjointness. We want to check that the subspace of F is disjoint from the orthogonal of a given space of functionals. Yeah? And that can be checked by looking at the matrix and seeing whether it has full column rank. Because in general, this will be a rectangular matrix now, not a square matrix. Yeah? And this is a special case. So, right, huh? Regular boundary, regular generalized problem. Okay, first and second is reversed. Yeah. Good, yeah. Projectors are also generalized inverses of a very special kind, yeah. And also this result about how you can construct a projector can be generalized to the case where the projector is specified by giving its image, U, but instead of giving its kernel, I only specify that its kernel should be a superspace of the given B. And so I have some choice here in the construction of this projector. But otherwise it's similar. Only in the regular case I had here an inverse, but here this need only be a left inverse. Okay? So I don't want to go into the details here with the transpose map. The idea of the transpose is only that whatever you say for the left side can also be said for the right side and vice versa by moving to the dual space. Okay, that's the usual principle, and this means this can be done in full generality to get the duality principle for generalized inverses because you see here when you have an orthogonal, you always change between T and its adjoint image and kernel is exchanged and then if you reverse all arrows and left and right and plus and intersection, etc., you always get from one valid statement to another, so you get, so to say, one for free. So, now what is a generalized boundary problem? The starting point is what we call a semi-regular boundary problem. So again, you remember a boundary problem was a map that is surjective. We keep this requirement here. And a boundary space is a subset of V star, which is orthogonally closed. Yeah? And regularity meant this direct decomposition. Okay, that's the boundary problem interpreted functionally. And the first part of this condition, because these are two at once, the first means the existence of solutions for every forcing function, and the disjointness means the uniqueness of the solution then. And now semi-regularity means that we just require uniqueness. So we only take the second condition here, that this is disjoint. Okay? So this means that we may not have solutions for all forcing functions, but if we have it, then it will be unique. So it's an overdetermined problem. And as I showed you before, we can check this condition of semi-regularity by looking at the evaluation matrix. And like in the regular case, a necessary condition was that these are equal. For semi-regularity, the corresponding necessary condition is that you have to specify at least as many boundary conditions as the order of the differential equation. So, having a semi-regular boundary problem, you can now add an additional piece of information, which is this so-called exceptional space, and this corresponds exactly to the setting of the outer inverses. You specify now a complement of those functions that can actually be reached. This T of B orthogonal, those are the functions for which we can solve the boundary problem. Because B orthogonal, that's a function that satisfies the boundary conditions, and then if I act with T on it, then that's a possible F. That I can solve. But then there are others, and which others? This I have to decide by choosing a complement of this space of admissible functions. Okay, that's the exceptional space. And then I call this, so if this holds true, this direct decomposition, then I call this a regular generalized boundary problem. So it's now a triple, no longer a pair. And its Green's operator is simply the outer inverse corresponding to these two spaces. The space of functions satisfying the conditions and the exceptional space E. That's the Green's operator of a generalized boundary problem. And again, I use this reciprocal notation, even though in this case I cannot offer you a localization, at least not yet. And the plane boundary problems are a special case where the exceptional space is simply zero, because if you have a direct sum already of the kernel, then the only choice for the exceptional space will be zero. And as you would expect, the Green's operator in the old sense coincides with the Green's operator of these triples here. Okay? And also this decomposition generalizes here that we had before in the setting of outer inverses. You have also this decomposition, which generalizes the regularity. For a regular plane boundary problem, we would have the kernel of T here. And here it's something bigger. Okay, and now it turns out that every semi-regular problem contains a regular problem, which I call the regular core. So if you have a semi-regular problem, there's always a sub-problem which is regular. And in addition to that, you can use it to compute the Green's operator by first projecting with this projector that I showed you before, and then you just do the Green's operator in the old sense of the regular core. And there are, of course, many regular cores in general. And the question is now, how do you compute a regular core? So, meaning, how can you compute some of the conditions here? And this you can do with a suitable projector. So here's an example. And I showed you a similar example already in Maple here. We have a second order differential equation here with three boundary conditions. Okay? And if you look at the subset of boundary conditions u of 0, u prime of 0, then that would be, of course, a regular boundary problem, because it's even an initial value problem. And also, if you choose the other set, u of 0 and u prime of 0, no, sorry, if you chose u of 0 and u prime of 1, then this would also be regular. But if you choose u prime of 0 and u prime of 1 equals 0, then this is not a regular boundary problem. So this would not be a regular core. And that's actually the typical situation, because in an application, most likely, you would get this second-order equation with just these two boundary conditions. And then you would realize, oh, that's not a regular problem, because it imposes a constraint on f, and therefore, to make the description unique, you have to add another condition. So you would add this condition that u of 0 is equal to 0, for instance. Yeah? So that's where this condition comes from. So if you write down the evaluation matrix here, you see that it has full column rank, so that's a semi-regular boundary problem. And that was the regular core. So we can use the previous result to compute the Green's operator here. It's trivial to compute the Green's operator of the initial value problem, that's just a squared. And now comes the point where we have to choose an exceptional space. Yeah? So here it's easy to find out what's going on. Yeah? Because of this condition that u prime of 0 is 0 and u prime of 1 is 0, you see that if you integrate this equation from 0 to 1, then you have on the left-hand side u prime of 1 minus u prime of 0. Okay? But that's 0 because of that. And that equals integral of f of xi from 0 to 1. So that must be 0. So that's the compatibility condition here. That's the constraint that f must satisfy, and only then can we solve it. Yeah? Okay? And now we have to choose an exceptional space. So we have to choose a complement to the space of those functions that satisfy this compatibility condition. And a natural choice would be the constant functions. Yeah? Because you can write, if you subtract the average of any function, then it will satisfy this constraint, so you just need a constant to correct it. Yeah? That's a possible choice, but you could also use another function like x here. Yeah? Then this would also give a regular triple here, regular generalized problem. Yeah? So in the first case, you get this projector, and the Green's operator, the generalized Green's operator, comes out like that, and you can do something similar for any other legitimate exceptional space. So what are now the compatibility conditions in general? So here, it was easy to guess the constraint, because we saw, oh, let's just integrate this, and then we see that this is 0 on the left-hand side. But of course, in general, we want to be able to compute, to determine this condition or conditions algorithmically. Okay? And so let's first define it formally. What are the compatibility conditions? So I have here a boundary problem. Need not be semi-regular in that case. Yeah? Then, first of all, this space here is the admissible subspace. I had this before. Yeah? The B orthogonal, these are the functions that satisfy the boundary conditions. I apply T to it, so that's a legitimate forcing function, an admissible space of forcing functions. Yeah? And now if you take the orthogonal of that, then these are the conditions that the admissible functions satisfy. Okay? So that's the compatibility, the space of compatibility conditions. It's the subspace of the dual of W. Okay? And the question is now how you compute this. And just maybe also note here that the point is that even though the admissible subspace is an infinite-dimensional space, but when you go to the dual space again by the orthogonal, then in the ODE case, you get, again, a finite-dimensional space. So there's a finitary description possible here. And before, we had this compatibility space here. Okay? And you can also count the number of conditions that you will get by just looking at the dimension of B and the kernel of T. Yeah? So it's this difference between the conditions that are prescribed in the problem minus the kernel of, so the order essentially of the differential operator. Okay? So here it's 3 minus 2. Yeah? That gives one condition. So how do you determine this? One way to do it is you choose any right inverse of T. And again, if you solve the initial value problem, that's an easy choice. And then the C can be given, the space of compatibility conditions, as the intersection of the given space of boundary conditions and the orthogonal of the kernel. And there are algorithms which compute this intersection. I think I won't have time to show you this algorithm, but this is algorithmic. And the G star applied to it just means that you add on the right-hand side of each of these each of these conditions at G here, and use the rewrite system to reduce it to normal form. Yeah? So that's of course also algorithmic. Okay, and the dimension can also be written like this, and and it turns out that if you have finitely many conditions, like in the ODE case, then the number of compatibility conditions is just equal to the dimension of the exceptional space. Okay, and for plane problems, of course, automatically you get that there are no compatibility conditions, as you would expect. Okay, so for semi-regular problems, it's even easier. There, you just do the G tilde star of B, where G tilde is the Green's operator of the regular core. Okay. So what's now an example of what happens now? Because actually, I said in the beginning that I only want to have a condition on uniqueness. Yeah, I still want the solution to be unique. The only thing that they allowed was that there may not be a solution for every forcing function. But I could also look at boundary problems where even this condition is not satisfied, that the solution is determined uniquely if it exists. Yeah? So what can you do here? And it turns out that it's always possible to extend this. That's why it's not mentioned in the main theory, because it's just an easy extra step here. So if you have any boundary problem here, now with no restriction whatsoever, then you first determine the compatibility space. And now let's assume that this condition of semi-regularity is not satisfied. Then what you can do is you can expand the given conditions in such a way that this becomes disjoint. Yeah, that's possible, but the trick is you should do it in such a way that you don't get any new compatibility conditions. Okay? So you add only as few new boundary conditions as necessary, no more. And that means that the compatibility conditions should be the same as before, and that is always possible by using a suitable basis. Yeah. For instance, here, yeah, that's a problem that is not semi-regular. If you choose this, that would be fine. But if you would add both, then you would have a new compatibility condition which was not there before. Yeah? So that's the moral here. Just add as few as possible. Okay? And that's the reason why here I restrict myself to semi-regular problems. So now the multiplication of generalized boundary problems, maybe that's something that I will go through very quickly. So you know the situation of the regular plane problems. And the message here is just that as you move to generalized boundary problems, many problems arise. Yeah? It's not as easy as in the plane case, yeah? Because regularity is not preserved, the reverse order law fails, yeah, in general, and there are some. It's difficult to get good conditions here. Yeah? So Anja did obtain some nice conditions for regularity that work for the setting here for the boundary problems. But in the general setting, when you forget, because you can do all this also in a very abstract sense, not thinking of boundary problems at all, but just about linear maps on vector spaces. And there's already a lot of literature on that. And there it is well known that this is really a difficult problem, yeah, to analyze this reverse order law for various kinds of inverses. Okay, so if you have this property, the fact that this reverse order law holds for some notion of inverse, this is a difficult problem. Okay, and here there are some results on that, yeah, that will guarantee this, but maybe I'm not going through this. Yeah, this is all rather technical. Yeah, but this is really, some of these results are really very nice and not yet known, and are also interesting apart from boundary problems. Okay, so let's just skip that here. The bottom line is that you can introduce a generalized product in this form. So here are two such problems. Now this part is very similar, except that initially for plane problems we had B2 plus T2 star of B1. But now we have to do in addition this intersection with the second exception space. And there's now a new component here which is symmetric to the boundary condition component. Okay, That's the exceptional space of the product. So that's the product. And again, you get back the usual problem if all exceptional spaces are trivial. And the reverse order law is now the real problem. Yeah? It says that you have this expected reverse order law if you know already that this is an outer index. Yeah? So that's the trick here. Yeah? So that means you need additional conditions that will guarantee this in some cases. Yeah? But there are some such conditions that are useful, yeah, for our purposes. But I don't want to go through this now. Yeah? Additional problems even with this semi-regularity. Yeah? In the plane cases, everything is so simple. Yeah? You multiply two regular problems, it's ensured to be regular again. Why? Because the Green's operators are just are just right inverses of the differential operator, and therefore, if you compose them, then also the composite will be right inverse. But that is not true any longer here, and that's why everything is a lot more difficult here. And there are cases where you multiply two regular problems, and what you get is not the regular problem anymore, and and then it's again a difficult task to ensure good conditions that will give you a regular problem. Yeah? And here's an example where the reverse order law fails. So that means that even though the product is in this case a regular problem again, regular generalized problem, but nevertheless the reverse order law doesn't hold. Yeah? If you check this, yeah, then here this is the Green's operator. Here I'm just multiplying two problems, two identical problems. Okay, so that's the product of the Green's operators. And that is the Green's operator of the product. And they are not the same. Yeah? This reverse order law fails. Okay? And there are again some technical conditions that will ensure that the reverse order law holds. And okay. Yeah? And now you can imagine that also factorization is a lot more difficult in this case. Yeah? That's the classical case here, where we have this, this description, precise description of the factors. But you cannot expect anything like that here, because in the generalized case, you will lose some information in general here because of the intersections here, and also there are now interdependencies. If you choose the B1, then that influences the choice of E1, because there's the constraint coming from semi-regularity, and same for B2 and E2, and also the reverse order law makes the choices of B1 and E2 depend on each other. So there's nothing yet which gives really a comprehensive result, but there are some nice special cases here, like this one and that one. Yeah? But again, I just don't want to go into details here. And also the case is important where the right factor is a plane problem. In that case, in that case, you can write it very nicely in this form, and you can also compute the boundary conditions of the left factor uniquely. Okay, so some of these algorithms here, they are just really reformulations of theorems that I have showed you. For instance, this. The intersection. I didn't show you the intersection. Yeah? So that's the algorithm that really computes these intersections that I showed you before. And fundamental right inverse, yeah? That's what I showed you before in detail, how to do the compatibility conditions, etc. So that's more for reference purposes, okay? So, but now I have maybe 10 minutes left or so.
More than that.
Maybe a bit more even, yeah? Then I can go back to what I have left out in my previous talk on the application that we did in actuarial mathematics. And that actually came to us from the actuaries when I was still in Linz. That was in 2008 or 9, yeah. Some people in the other group of our institute, actuaries, came to us and said, don't you have some things for computing inhomogeneous, actually first they thought of homogeneous, yeah? And then we said, don't you have inhomogeneous ones? And that's crazy. Normally people are much happier with homogeneous equations. Why do you want inhomogeneous ones? So, yeah, then we can compute Green's operators. And they said that they have something like a boundary problem coming from insurance mathematics. And that takes a while to understand where that comes from. So if you have an insurance company, the crucial question is, does it go bankrupt or not? Yeah, that's an interesting question for the company. Okay, and a very simple model is like that. Yeah, so here's time on the horizontal axis, and here is money. Okay, units of dollar if you want. Yeah. Now the insurance company starts with some initial capital U. Okay, and now its clients will pay premiums for their car insurance, etc. And here the simple model is that this comes in at a constant rate, just the capital accumulates, but then somebody has a flat tire on the highway, for instance, and goes to the insurance and says, yeah, now I need some money, they have to pay. And that happens from time to time. So you have this random process here, and then at some point it may happen that they have to pay more than they have left. So that's the situation of ruin. Okay? And then there are two crucial parameters here, which are called the surplus before ruin, okay, and the deficit after ruin. So usually they like to make these functions continuous on one side. I always forget on the left or on the right, and then this would be the left limit and the other one would be the right limit, but don't ask me which is which. Anyway, so these are the two crucial quantities, okay? And the usual model is that this is a kind of Poisson process or something, but yeah, I can show you the assumptions here. But now the question is, how do you come actually to a boundary problem here? So that's this picture again here. So this process is the distribution of the claim size, how much this is on average, the distribution of when it happens, that's just assumed to be distributed identically and independently, okay? And typically an Erlang or Poisson Erlang distribution, okay? So that's the capital written in terms of these random variables. And the time of ruin is the crucial quantity. That's the first time when this becomes lower than zero. And the ruin probability is under the condition that the U of 0 was the initial capital U. What is the probability that this quantity here will be finite? That this ruin will happen. That's the ruin probability. Okay? And a basic assumption that this whole thing is fair, so to say, that the company even has a chance of not getting ruined
is it the expected value?
Yes, that the expected value of one claim, this time between two claims, multiplied by the premium, this must be larger at least than the expected value of how much they have to pay.
What is C here?
C is the premium rate, how much they get per time unit. Okay, so that's the condition that it makes even sense to think about ruin probability. Okay? Now the Gerber-Gio function is a kind of elaboration on this quantity here. The ruin probability is, so to say, only the rawest measure. The most important thing you want to know, how big is the probability, so to say. But to have a more refined notion, you want to take into consideration the x and the y here. Okay? And that's the idea of the Gerber-Gio function. Okay? So the exact definition...
Are they interested in the joint distribution?
Yes.
Okay.
That's right. That's here. That is the joint distribution here.
Okay.
And what they're interested in is a kind of weight function or a penalty. That's the penalty that says that depending on what you want to measure. If, for instance, if you want to measure moments of this surplus before ruin, then you would choose a w of x and y, x to the k, for instance, or moments of the other one, or whatever you like. This just, so to say, specifies what you want to take into consideration most and what not so much. That's the penalty function, which you integrate against the joint probability, and that's just a discounting factor which helps convergence and somehow it has the sense of that inflation is modeled in some sense.
I'm trying to catch up with the notation here.
Yeah.
So x is equal to u of tu dash. What does that mean?
That's the surplus before ruin. Yeah, that's just this. That's the left limit of the time.
That minus sign means limit.
Yeah, that's the left limit, and that's
the right limit.
That's so to say the right limit, but it's assumed right continuous apparently. So that's just u of tu. Yeah, but I mean the picture is more helpful.
Right.
Yeah. Okay. Yeah, they just like to write everything very complicated. Yeah, that's how the actuarials write it. Okay, yeah, so that is the Gerber-Shioux function, yeah? And you see that it is actually not a function, even though they call it like that, it's an operator, yeah? It's a Green's operator, because it takes this function, W, and makes a new function from it, yeah? Which is a function of U, yeah? And that's the Gerber-Shioux function, okay?
Why isn't the capital X is not involved in here?
Capital X is involved because this joint distribution has it, this here is the joint distribution of this.
Maybe it's T
here, yeah. This TU here. If you go back, the TU involves
infinite of
here.
U.
Here
Okay,
it involves
there it is.
yeah?
Okay, there it is.
Yeah. Okay, yeah. So that's the original definition by Gerber, the Swiss actuarial mathematician, and Shioux, the Chinese actuarial mathematician. Huh? That's why it's called Gerber-Shioux function.
Around when?
Not so long ago, maybe 5 to 10 years, I think. Yeah. Something like that. Yeah. We were meeting Gerber at the conference in his honor in Linz in 2009, I think, or 10, yeah? or 2009. Yeah. So what we need in the end is, of course, this kind of boundary problem formulation. And here what is a bit confusing for me is that this function is not called U, because U is already the capital, according to the notation. So that's now M, the Gerber-Shioux function, and some boundary conditions, yeah? And now the question is, how do you get the differential equation and how do you get boundary conditions? And I just want to be very fast here. You assume that the distributions of the time and the claim sizes are what is called phase time. That just means that these distributions are characterized by an ODE with constant coefficients, or the Laplace transform is a rational function. That's how they usually say it. Yeah? So like Erlang distribution and things like that, exponential type things. Yeah? But that's a very common assumption. And then with a certain renewal argument, yeah, you look at the convolution, because that
so the
represents the sum of random variables.
What is a partial?
No. That's just the distribution of tau.
Okay. That's a function of tau. Okay.
Yeah. And so you get an integral equation from this definition by a renewal argument. I don't know the magic behind this. That's just probability. Yeah?
Right.
But essentially, it's the integrals enter because the convolution means the sum of two random variables. Okay. And then with another magic that one of our collaborators, Corina Constantinescu, has applied in her thesis, 2006, yeah, you can extract from the integral equation an integral differential equation using something a bit similar to Lie groups, but more general in some sense. It's continuous semi-groups here. But again, there's a notion of an infinitesimal generator, and, so you can use semi-group methods on that. And that, in the end, gives an integral differential equation, and then usually integration by parts will get rid of the integral. In this case, it's possible. In general, it's not always possible, but here you get a differential equation, and that will be more or less the forcing function here, and the differential equation is essentially the differential operator annihilating the time distribution, the adjoint of this operator. And here multiplied by the annihilator of the differential operator of the claim size distribution. Yeah? And the F, the right-hand side, is this here, which is more or less the penalty function, yeah? Just modified a bit. Yeah? And then to get the boundary condition, we had to compute the initial values. But in addition to that, this condition comes from the net profit condition, which I showed you before. Yeah? This inequality is equivalent to the fact that the Gerber-Shioux function, if you wait infinitely long, so to say, is zero. Okay? So it's very specific kind of boundary.
I thought the argument for M was the initial capital.
Oh, sorry. That's right. Yeah, no, that's my mistake. Yeah, that's right. Yeah, so for infinite initial capital, this is here 0. Yeah, right. Yeah, and here the mathematical setting is very simple. Yeah, because this is really a constant coefficient differential operator here. If you substitute all these parameters, yeah, it's just constant coefficient. But the tricky thing is that they want a solution, closed form solution in some sense, which is generic in the order n. They want to write it down for general n. Okay? And then the other tricky thing is that since this boundary condition is at infinity, it's not a compact interval anymore, like in a two-point boundary problem. So you have, if you have exponentials in the integral, then they will not always converge. So you have to distinguish between those cases where the real part is positive, which means that when you integrate, this diverges, and those where the real part is negative. Yeah? And that's why it's an unusual situation that you have, even though that is of order m plus n, you have only m plus 1 conditions. Okay? But somehow these m plus 1 conditions hide more, because even though you have more undetermined parameters as coefficients of your exponentials, those that are in front of an exponential with a positive real part, they all have to be 0. Otherwise, this would not converge. Otherwise, this condition could not be satisfied. Yeah? So this one condition...
Why can't you replace infinite by a huge number?
I don't think you would get... I mean, you could get an approximation, but...
practically, for practical... You know.
Because they would like a formula which they can type in, which is...
put a couple of trillion in there.
Yeah, but I don't think it would be faster to do it, yeah? Because here, if you don't make this assumption, but you just distinguish carefully the positive and negative real parts, then you get a symbolic solution which is exact and which is easier to use. Yeah? So, but you're right, yeah? If this were not possible, then this could be an option. Yeah? That's right. Yeah? Okay, yeah? So I don't want to go into details, yeah? But just the point is that now we had to use a different function space here of 1 times differentiable functions of compact or of vanishing at infinity. Yeah? So the additional condition is that the limit of this as x goes to infinity is 0, and these initial values were also quite some work to compute, because again there was some strange fundamental like determinants. But in the end, this is the result that we got, where you need a Laplace transform. So the notion of what is a closed form solution is a very relative one. Yeah? But for them, it was explicit and closed form enough. Yeah? And well, I don't want to go into all these generalizations then. Only maybe just one point is that in the second paper that we wrote with this group, the main innovation was from the applied point of view, from the insurance point of view, that this capital doesn't just increase linearly, but you have some interest rates modeled by this integral here, okay? So if you use P of u equals a constant function c, then you get back again c times t, okay? But here it's more general, yeah? And mathematically this means that in the end you get the differential equation with variable coefficients. So in that case you don't get anymore a closed form solution, only in some special cases, and otherwise asymptotic results can be shown. And that's also useful for them. Yeah? So that's just the basic idea of how we were able to, and maybe also what is really the point here. Yeah? Why was the Green's operator approach important here? It was important because they wanted something which gives the Gerber-Gio function for arbitrary m, where m is the order of the differential equation. And that's important to them, because the m somehow models the, I don't know enough about this, but somehow the statistical quality. Yeah? The m can be made bigger and bigger because it describes in certain scenarios a more realistic model of the probability distribution. Yeah? And therefore...
Do with the number of subscribers or something like that? Does it have something to do with the number of subscribers?
Subscribers to what?
To the insurance.
Yeah, that maybe there's some. They never explained us this very much, but supposedly, yeah. But what we could use here is, of course, a decomposition of a factorization of boundary problems. Yeah? So this boundary problem of order m plus n is factored into first order problems. And then you solve just the first order problems, rings operators, multiply them together, normalize them, etc., and you get the end result. Which is interesting because when I once talked about this in Linz, somebody remarked, who on earth wants to factor differential operators? Because in physics, all differential operators are second order, maybe third or fourth order, but never higher. So why should you care? And somehow it's true. The factorization only becomes powerful, I think, if you have, like here, either applications from within mathematics or applications that don't come from physics, but like from economy or insurance.
T up there, right?
Yeah.
Isn't that the number for the order that you want to do?
No. This T is time.
Related to that?
That's time.
Yeah, but is n of T? That's a number. There's a number dependent on time.
Yeah, that is the number of insurance cases.
Exactly.
That's the number of such zigzags.
Right, that's right.
Yes.
So I think that might have to do with this order here.
No, because the n of T itself, the n is again distributed Erlang m, for instance.
Okay.
So for each choice of m, this will give you a random number n. So
okay. M is what now? I forgot.
I always mix up m and n.
You have two m's there. And then.
But one is, so in general, so this is, maybe this is m or n. Each of the x is distributed Erlang n.
Right.
And it could be that m and n are swapped here, sorry.
Those are IID.
But yes, Yes, each of the x's is IID.
Now, do you need to know the John distribution of u?
I think they have computed that, but that was not in our hands. That's something.
Because there is a theorem that it's called Spitzer's identity.
Yeah, I know that. That's essentially a case of Rosenkranz.
The Rosenkranz, but that's also really computing the John distribution of independent. Sums of independent.
Maxima of running sums. Yeah, that's right. That's right. I should really discuss this with them. Yeah, that's right. I never had this idea.
That's where the whole thing comes.
That's right. It's why Glenn Baxter did this
fluctuation theory.
That's right.
That's really
I have to ask
this
them.
is going on. Seems.
Right.
I mean, I don't have a hunch, of course, nothing.
Yeah. But for us, I mean, this was really a nice collaboration, and it's still actually ongoing, because the next scenario that they want to discuss is now to add taxes. And that mathematically means you go to a PDE, but a certain kind of, simple kind of PDE, and again, with boundary conditions, and we are just working on that.
See, the nice thing about the Spitzer identity, I don't know, related, is that it was, it's actually an expansion, and then summing up into just one single term.
Yeah.
Or a whole series of iterated integrals, which give you the joint probability.
Right.
So I mean, if you really want that thing to be for any order, it might. I mean, that's some exponential on the other side of the Spitzer identity, which might.
I really have to ask Corinna.
It's almost like. I mean, to me, it's almost like a what's that called? When you sum a power series, what is that? Generating function.
Yeah.
It might be a generating function for the joint probabilities. That's how I try to understand the Spitzer identity. Now, of course, you have other terms there too, but that's something fixed. I mean, the first two terms are something fixed, right?
Yeah.
That you don't have to worry about.
That's right. Yeah. That doesn't involve the random processes. It's a recursive description.
Yeah, right.
It's this U of S.
Yeah, exactly.
Yeah.
So that might be related somehow.
Yeah, I have to ask them. That's an interesting idea, because that would be another nice connection that I had not contemplated before.
They might say, that's exactly what we're using.
Yeah.
Who knows?
Yeah, maybe. But maybe there's some additional insight that can be brought into this. Okay, yeah, so, I mentioned this, that I want to do this with the PDEs, etc. Yeah? So, thank you very much. Yeah?
Okay, thank you.
My pleasure to be here and share some of our work.
Any questions?
No, that's a lot to absorb here.
Yes, I'm sorry.
Sure, no, there's a lot of
stuffing in too many things.
Well, no, this is great. This is great.
But maybe
I like
on the slides, you can.
With the slides and the
contemplate
talks
it,
online, I'll be able to.
Very good.
Thank you for assisting.
Thanks everybody for